Hi, everyone. Welcome to the Sense Think Act podcast. I'm the host, Audrow Nash, and in this episode, I'm talking to Erik Schluntz, co-founder and CTO of Cobalt Robotics, which makes indoor security guard robots. Erik and I talk about having the Cobalt robot take elevators, how Cobalt has humans help their robots make decisions, robot body language, advice for entrepreneurs, and several other things. It was great to talk to Erik. I enjoyed learning about how Cobalt uses humans and robots in their systems, which each play to their strengths. It was also great seeing how Cobalt Robotics has navigated getting investors and funding. As always, a big thank you to our founding sponsor, Open Robotics, and I hope you enjoy. All right. Hi, Erik. Would you introduce yourself?
Hello, I'm Erik Schluntz. I'm the co-founder and CTO of Cobalt Robotics.
Would you tell me a bit about Cobalt?
Absolutely. So Cobalt builds indoor security guard robots. So these are robots that will patrol around an office building looking for anything out of the ordinary. We work with human operators to help support the robot. So if the robot comes across anything it doesn't know how to respond to, it switches over control to our humans, and then our humans can escalate exactly like a human guard on site would, whether that's calling the customer, calling the police, or having a friendly video chat and sort of asking how someone's doing, just like a security guard would.
Nice. And so for the people listening, would you describe what your robot looks like? And how do we refer to it? What do you is it the Cobalt robot or
It's
what do you
just
call
the
it?
Cobalt robot. We actually we decided we didn't want a separate product name from company name. That can be hard to brand both of those. So it's just the Cobalt robot. And, I'll describe this actually while playing a video for people that are watching.
Sure.
So we'll get this going here. So the Cobalt robot is about 5 feet tall, and it'll patrol around. It has wheels, 2 main drive wheels, and then 4 supporting casters. It's designed to navigate around through an indoor office space, looking for anything ordinary. That can include doors or windows that have been left open. The body is actually coated in fabric, so it's a little bit soft and squishy. And this was actually a big part of our industrial design, was that we wanted the robot to be friendly. The job of a security guard is to keep people and employees feeling safe and comfortable. And so if the robot is scary, it really hasn't done its job right. There's also a touchscreen on the front of the robot that we use for being able to interact with anyone around the robot, where one of our human operators can video call and talk to a person on site. We also have a lot of sensors, cameras that are 360 degrees around, so no one can sneak up on the robot, and then a ton of sensors that you'd find in a self-driving car, like LiDAR and depth cameras and IMUs.
So how I'm thinking of it, it's like a telepresence robot that has a lot of sensors that makes it more sophisticated. And then you have the whole like person in the loop thing, which makes it a good bit more sophisticated. But is that a squishy, basically a telepresence robot with a kind of cylindrical fabric body?
Yeah. And I'd say that's what our design is, basically, that it's telepresence 5 or 10% of the time and autonomous 90% of the time.
Okay. Now, and the one behind you has a little arm.
Yes, yeah. So this is one of our add-ons for some of our customers. For our security patrols, we want to be able to patrol through multiple different floors. And so to do that, we need to ride elevators. Now, in the past, we've done elevator integrations that are wireless. Those take a long time. Elevator companies are often very slow. And so actually what we do now at a lot of customer sites is just physically press the buttons. So we added a 1 degree of freedom actuator that can swing up and press the elevator buttons. And we use the cameras and computer vision to detect the buttons, know where we should press. And we actually have this rolled out at a bunch of customer sites now. And it's a lot faster to roll out than a wireless integration, and it works pretty well. So yeah, I'll show a video of that for people, and I'll kind of narrate this. So the robot first starts and presses the button on the outside of an elevator, waits for the door to open, navigates inside. Elevators are a very technically challenging thing to do. We find tons of things like elevator thresholds that are actually out of spec that would cause a lot of problems for people in wheelchairs that we need to deal with.
What do you mean? Is that like a big bump getting into it?
Exactly. Or what? We find elevators where it's a 2-inch gap, between the elevator car and the floor, or, a 1-inch vertical. But once the robot gets inside, it uses computer vision to see the button panel and know which button it should press. selects the correct button, drives forward to press it. And as I mentioned earlier, this arm that we add is only a single degree of freedom. So we actually use the robot's drivetrain to steer the robot left and right and to move forward and backwards. The arm only moves up and down.
Yep.
And we use the robot for the rest of the degrees of freedom.
I think you mentioned, so it has, so the Cobalt robot has differential drive or something, so you can turn. It's not omni drive, so it doesn't move side to side.
Yeah, it's differential drive. So we have 2 main drive wheels and 4 support casters.
Okay, is that tricky to get lined up with the button, or?
Yes, so we definitely put a lot of work into sort of that motion control and planning to be able to nicely line up and press a button, especially because elevators often have very tight spaces. So we don't have a lot of room to sort of back up by 10 feet and approach it nicely. We have to kind of operate in these very tight spaces.
Gotcha. I wonder, do you have ever the situation where if the elevator is so tight that you have to raise the arm and then kind of swing into it?
We haven't hit that yet, and luckily there are rules around elevators, mainly for people with wheelchairs. So we can actually just follow a lot of those same design specs to know what the robot hardware needs to be capable of.
Gotcha. And is it difficult when you go into a new elevator to find the buttons? Like, I imagine that this is fairly custom, depending on the use case, depending on how you're detecting things. Yeah.
So we have a sort of a proprietary system that we've set up where one of our sales engineers can go on to a new customer site with the robot and very quickly calibrate the robot for that site. So we don't need a ton of training data or anything new like that. We can kind of just bring the robot through the elevator once, and then after that, it's able to use the elevator by itself.
Ah, that's awesome. You kind of, can I guess at what it is, or?
Yeah, sure.
Do you use the depth camera at all in this for figuring out how far away you are? And
we mainly use the LiDAR for that. One of the other interesting challenges is that elevators are very reflective surfaces. A lot of times you have sort of the polished metal, and time of flight depth cameras can do very poorly with that.
Because so they're shooting out infrared and trying to see that, but then it bounces off, so you don't get any good depth information, maybe very noisy depth information.
Yeah, you get very noisy, but the LiDAR at the bottom of the robot is pretty good, and we know that in an elevator, it's a fairly structured environment where we see the walls is usually in line with the buttons.
Why is LiDAR more reliable? Intuitively, that doesn't make much sense to me. So for the depth cameras, are they structured lighting where they're projecting something out and then trying to observe what that is? With the pattern and the deformation in it, or?
That's a great question. So the one we use is not structured light. It's time of flight.
Oh.
And I don't think there's any inherent reason that a time of flight depth camera is worse than a LiDAR. But typically what we see is that LiDARs are a lot more powerful and you just put a lot more watts into those beams to get a much better signal response.
Gotcha. And the LiDAR of this robot is it's like on the base,
it's at
right?
It's at the very bottom of the robot. And it can see around 270 degrees around the robot. And so that gives us kind of a good sort of footprint of what the room that it's in. Yeah. And then we use the optical camera on the front of the robot and can get very good sort of optical readings of the buttons and see where they are.
Yep. And then how do you control the press for this? I'm imagining like you basically raise that to the correct height that you imagine the thing is at, and then you just drive forward until you hit some sort of...
We drive forward, and we have a sensor at the very tip here to know whether we've made contact.
Cool. Little force sensor?
One of the... initially, we had a force sensor, and then for reliability, we just switched it to a switch that's calibrated. And yeah, one of the interesting things is sort of we can tell that we've hit something, but you don't necessarily know whether you hit the button or the rim of the button and maybe didn't engage it. So there's some interesting things we can do to sense whether we've hit that. One of the first things we thought of is, we can tell whether the light turned on the button, but you'll actually find plenty of elevators that don't light up. And so actually what we do now is we wait for the
accelerometer or something
of the acceleration of the elevator.
So if you feel it moving.
Exactly. That's kind of that's like the ultimate end goal is we feel like the elevator is now moving. We know that we've correctly told the elevator what to do.
Now, is there ever the case where the robot is in the elevator, pushes the button, but misses? so that it didn't actually click the button, and then someone calls the elevator from a different floor and it sees it
There
moving?
is. Absolutely. And so I think what you brought up is that one of the really interesting challenges of this is that when we are in an elevator, in the worst case, we're inside a Faraday cage. And so this behavior has to be 100% autonomous.
Wait, speak about a Faraday cage for just a little bit.
Yeah, absolutely. So a Faraday cage is a closed metal structure that no radio waves or electromagnetic waves can get in or out of. And so that means that for some elevators, when we're in them, we don't have Wi-Fi or cellular. And that means that we can't rely on our human operators that generally we use for our supervised
that's hard because it's like one of the more difficult situations, and
exactly,
you're in a Faraday.
Exactly.
You're in a Faraday box. That's crazy.
Yeah, so it's very funny. But and generally what we say at Cobalt is that one of our sort of really fun advantages for our engineering team over, say, working at a self-driving car company is that we just have a lot of inherent safety and stability, that we move slowly through indoor spaces. If anything happens, we can just stop and call a human operator. You can't do that on a freeway. And so that means that we can basically solve for the 99% case, and we don't need to worry about solving the last 1%.
You bring in a human
except
then.
in the elevator.
Except in the elevator.
That's where we need to aim for that 100%.
What do you mean safety and stability for this?
Yeah, safety and stability.
And stability.
That, we're not. Yeah, we're not trying to balance on two wheels. It is always a safe situation for the robot to stop. And so we can take a lot of advantage of that and basically handle covering a lot of edge cases with that safety behavior of stop the robot and wait for a human operator. Except in the elevator.
Oh.
Then we need to find a way out of it.
Popped up. That's 2 interviews that this has occurred, so I have to figure out how to turn that off. Okay.
Yeah, I'll need to be careful not to say the G word over here to my phone. Basically we need to make sure that because we're in this Faraday cage where we can't call for help from an operator, that this robot is going to get itself out of the elevator come hell or high water. And there's all sorts of really funny situations you can get into. Like you mentioned that, perfect timing, you can miss the button, but someone else calls the elevator at the same time, so it thinks that it's succeeded. And we have really robust state machines that we've built around ththese behaviors, so the robot knows what state it's in and knows how to retry from pretty much any state, and knows that these kinds of things happen. That even though if it's felt the motion, it knows there's a chance that maybe this is just a coincidence. And if it doesn't go to the right floor, hey, I might need to retry and go somewhere else.
Okay, yeah, because what I was getting at with that is I'm curious about the mapping problem. So how you split up different maps, I suppose. Like maybe each floor is its own map, and then you try to, once you enter a new floor, try to figure out where exactly you are in it. So that, which am I on floor 1 or 3? This kind of thing.
Yeah, so there's I think 2 interesting things there. One is sort of knowing what floor we're on, and then the other is knowing where we are sort of inside the floors. For the knowing what floor we're on, we actually use the accelerometer for the robot.
So you integrate the accelerations to try to...
We do.
Did you? Yeah. And I suppose you decided not to use like a barometer or something like that. Was it too noisy? Or, not accurate enough?
So we explored a bunch of different sensors, including barometers. One of the things that we found there is that indoors, pressure is determined a lot more by the HVAC system
that's
than
interesting.
by your actual altitude. So you can go on one floor and the pressure can actually be lower even though it's higher because the air conditioning settings are different. So it wasn't a really good sensor for determining
that's wild.
Where we are. And so we did a lot of really interesting sort of looking at different sensor modalities for this. Now, the accelerometer, you're absolutely right. We're double integrating. And double integrating is always a scary thing. Because if you do it forever, you're going to either end up going to the Earth's core or going to the moon. And so one of the things there is that we can actually apply a lot of structure and constraints that we know about how elevator systems work in order to basically constrain that and add a lot of these checks that keep the robot from going to the moon or the floor. So an interesting one there is that that basically floors are basically integer divisions. So if you stop and you're kind of, I think I'm at floor 1.1, you can actually snap that down. Floor 1. An elevator never stops at sort of 1.5 floors. And similarly,
not if it's working still.
Exactly, not if it's working. And similarly, there's a lot of these other constraints that we found out while researching and testing on elevator systems, that they follow very consistent acceleration profiles and speed profiles. And we can use a lot of those things to basically add these constraints so it doesn't become an unbounded double integration. It becomes sort of a much more constrained problem that we're fitting to.
Yeah.
And we can then tell what floor we're on pretty accurately.
Gotcha. So you integrate your acceleration results. And I guess probably, so integrate, get velocity, integrate again, get position. And then you look at the position of the robot, how it's changed because it's moving. And then you get some sort of rough approximation of how much you've moved. And then you use that. So it's like weighted information. So you say, oh, it's probably about this.
Exactly, yeah. And we can use this extra information of, when we know that we've stopped, we can basically clamp it to 0 until we see more than a certain amount of acceleration. Because we know that when the doors are open, when we've stopped, we might be reading a little bit of acceleration, but we know that elevators don't actually jiggle around. If it's mostly stopped, it's
a terrifying elevator.
Stopped.
Yes.
Unless it's a terrifying elevator. Exactly, yeah. So basically, we found a lot of these hidden constraints that let us do this very accurately and filter and know what floor we're on.
Interesting. What if you have to go up 20 floors or something like this? Like it's a skyscraper. Say 50 floors, 80 floors.
There's definitely a point at which this breaks down.
I assume.
I'm actually not sure where that is, but we have not yet hit a building
where it does not work.
That trouble. Yeah,
and
we've been in some high rises in the San Francisco area,
and it still works fine. That's awesome.
Yeah.
So if you want to go if you want to go to like the 32nd floor, or how large are these high rises?
We've done jumps of 20 floors with good accuracy, and I've never tested above that.
That's awesome, though. Hell yeah, I'm impressed it works to that level, which is awesome.
Us as well. We were initially much more optimistic about the barometer than the accelerometer, and we were actually very pleasantly surprised that it works out. And again, you can do nice things like right before you get on the accelerometer, or right before you get on the elevator, you can pause for 5 seconds and zero out your IMU calibration.
Yep.
Because hey, unless there's an earthquake going on right now, I know that I'm not accelerating. Let me save that as gravity. And then, for a 5-minute elevator trip, that stays pretty good over that short period of time.
And then how do you store your maps? Is it like, so I'm wondering if it's so say you have 2 floors. Is it one map that includes both floors, or is it 2 separate maps, one for each floor? Or each like, I don't know, consecutive space or continuous space. Contiguous space.
So that's another really interesting question that we had at the beginning while working on this. And it's also an interesting question that ties into our HRI of how our operators and how our customers interact with the robot. Because this isn't just a robot operating in a vacuum. This is the operators and customers want to see where it is on the map. They want to see the alerts coming from the robot. And actually what we found, what they liked most was not needing to switch between maps and only being able to see one floor at a time, but seeing all of their floors laid out side by side, just like you would on a floor plan. And so actually what we do is we just have them on one giant map in different locations. And so a robot switching floors is implemented as just teleporting to kind of a new island in this map where it can go between.
Interesting. And the elevator is like the portal between all of these different floors. That's
exactly, yeah.
Okay. Now, so getting into the robot a little bit more.
Yeah.
So it has a bunch of sensors. Would you just talk a bit more about the sensors that are on it?
Yeah, absolutely. So there's, I'd say, 2 categories here. The bottom half of the robot is like an indoor self-driving car. And basically its job is mobility and safety, to bring the robot around through a customer space and get the robot anywhere it needs to be. And the top half of the robot is all about providing the security service that we provide to our customers and providing that value. And basically it's a mobile sensor package that can be brought anywhere. And there's a couple high-level goals there. The primary thing that we do for our customers is detecting people. If we're patrolling around a warehouse at 3 a.m, you want to know if there's a person, there
in the warehouse. Yeah.
And a lot of the times, they are supposed to be there, but we get an alert to our operators and they video call in and say, hey, excuse me, can I see your badge? Why are you here after hours? just like a security guard on site would say, and then they can authenticate them and make sure they're allowed to be there.
Mm-hmm.
The other big category of things that we do is facilities inspection,
Mm-hmm.
going and taking pictures of sensitive things, whether that's an expensive piece of equipment, either using our optical cameras or our thermal camera, or checking doors, sort of sensitive things like that, and also environmental checks. So we have temperature sensors, humidity sensors, carbon dioxide and carbon monoxide sensors in the robot. And what's really great is being able to move these sensors, this sensor package, around an entire building, and not just get sort of a single point measurement like you would from an air quality sensor, but being able to generate a map of air quality and being able to say, hey, not just what's the carbon dioxide in my office, but get that map and say, wow, the carbon dioxide is all coming from this corner here. We must have a broken vent. And basically taking that promise of what like IoT sensors are trying to do, and instead of needing 1,000 sensors, bring it everywhere and sort of localize that data on a map. And so we've helped customers catch really interesting things, whether that's broken HVAC systems that could possibly pose danger. We actually found HVAC issues with temperature, where we showed that one half of the building was like 5 or 10 degrees colder than another.
Oh, man.
And they said, like, oh man, we've had employees complaining about this for months.
Yeah.
And we didn't believe them, but now that we see the data from the robot. And so really what the robot is we want to bring sort of superhuman sensing to what a guard could do, and the things that a guard could notice while looking around, and that can be security or facilities.
Mm-hmm. Do you guys ever, so you have this arm now, and I feel like that's a relatively new thing to push elevator buttons. Do you ever try doors to see if it's a hinged door, to see if it's locked, or interact with the environment in any way with it?
So we have some interesting things coming out for doors in the next year. I can't talk too much about it,
okay.
But stay tuned.
Stay tuned.
Yeah.
Awesome. So,
and I will say with this, we can press handicap buttons to open doors.
Oh, that's awesome. Let's see. So with these sensors, now I noticed, so with all the air quality ones, basically, how did you select the air quality sensors? So you have like carbon monoxide, carbon dioxide, smoke, I don't know what else. How did you select the sensor packages and humidity and temperature? How did you select these ones for, as opposed to anything else?
Yeah, exactly. So at the beginning, sort of when we did a lot of customer discovery, asked our existing customers, what are the kinds of things you're worried about in your air? What are the kinds of things you want to know about your space that you don't have right now?
Mm-hmm.
And sort of took a lot of that input and then looked at what was feasible. We actually have a radiation sensor on one of our robots for one of our customers.
Oh.
So that's not a standard option, but we can add other sensors as needed for special cases.
Gotcha. I was going to ask about customization next. So you are customizing a little bit. I imagine, so with the body of the robot being kind of a big cylinder covered by fabric, it seems like you can probably have pretty large sensor payloads and you can swap them out fairly easily. So you mentioned the radiation one, but is there a good amount of customization that occurs, or?
Only for very large customer deals. We really try to stay away from as much customization as possible. The sensor package is one thing that's a little bit easier for us to do, but it's sort of, right now it's tied to sort of large new deals that we do with customers. I would say that the majority of what we do that's custom, I would consider more configuration than customization. So we can configure the robot with actually different color fabrics to match the customers. And a lot of the robot's behaviors actually are very different between customer sites. And one of the ways we think about this is that security is basically a big human configuration of if this, then that. If you see a person that doesn't have the badge, call this person. If you see a door left open, do this. And these are sort of the instructions that are given to human guards and sort of human security teams about how they should respond in all these different situations. And so our robots are very highly configurable for different customers. So for one customer, seeing a person might be just, note it in the daily security report. And for another customer, it might be immediately call the police. And so, there's these very, very divergent actions based on what the robot detects.
Yeah.
And we've built systems that let us very easily configure that. so that the robot can basically do exactly what your guard was doing.
Yeah. How does that work? So for you to customize the robot's behavior, um, how like are you using? Do you have users use like a block programming language, or is it just you tune a bunch of values? Um, how does this work? Or you maybe select from a drop down. If this occurs, then do this. How do you set this up?
Yeah. So we like to make things as easy as possible for our customers. And our customers, they just want security that works.
Mm-hmm.
They don't want to think about the robot or programming anything.
Yeah.
So typically one of our account managers, who is an expert in security, and also now an expert in our robot system, they will work with the customer and look at their existing instructions for their guards and basically translate it into our configuration for the robot. So the customer just has to give us their instructions as if we're a security guard, which they love, and then basically we turn it in on our side into this configuration for what the robot does.
So it's a fairly one-off thing done by an expert, is what I am hearing for this. So
exactly, yeah.
Huh.
And this is sort of pretty standard for how the security industry works. That every sort of new building or company, when they get security guards, they have an account manager that basically helps set what are the instructions for the security guard. What should they be doing on the site?
How detailed is it? Like, how many things to configure is it? Is it like a huge list, or is it a few simple if this then that statements? Or I guess it may vary.
Yeah, it varies. I'd say there's some customers that sort of are very new and young customers that are expanding, have their first few buildings, and we actually usually help them define sort of what their security procedure should be, because we've seen a lot of much more mature security programs, and help them sort of know, hey, well, what happens if this person doesn't answer the phone? Like, you don't want something to just stop, and so a bigger company will know, here's the whole call tree of how you escalate things.
Yep.
If someone isn't available. And for younger companies, sort of we help them define a lot of that same security program with the same rigor, so that we can help them get to that level.
Gotcha. That's cool. That's interesting. You guys are becoming security experts through this problem.
Exactly, yeah. And sort of for us, we have a big robotics team, and we also have a security operations team. And they're the people that are interacting with customers and using the robots and using our control interfaces to configure them and to respond to alerts and help keep the customer safe.
Yeah. So have you guys ever, kind of a silly question, but have you ever had a, where a security guard would maybe try to physically stop a person from doing something? Say there's like a thief or something. And they would tase the person. Is there any would you put a taser on the robot or on the little arm that comes up? Or
so there's no taser on the robot. I'm actually really happy you asked that. One of the little known facts in security is that a security guard will never touch a person. It's a huge liability issue. All they do is call the police. You'll actually see a lot of security guards that either have fake guns or unloaded guns.
Really?
And it's entirely for deterrence.
Whoa.
Because imagine sort of the liability if a guard misjudges and a person was actually an employee, but they thought they were, up to no good and tackles someone and hurts them. Be this huge liability issue. And so it's very funny. When we started off, this was one of our big assumptions as well. And this actually kind of gets to how we started Cobalt. When me and my co-founder, Travis Dial, started Cobalt, we actually didn't know what we were going to work on. We had both started companies in the past. We had both been through Y Combinator, and that's where we met each other. And we had seen a lot of people come up with a startup idea and then really get overly attached to it, despite it not really being needed by anyone. And so we decided that we were going to take the opposite approach. We were going to find a real customer and a real problem, and then work backwards to the idea. And so, he quit Google. I turned down a return offer to SpaceX with no idea what we were going to do. Both of our families thought we were pretty crazy, but we're like, no.
We'll
Having a startup idea is crazy. This is better. And so we spent the first few months interviewing people from different industries, anyone that we didn't really know what their job actually entailed. We wanted to talk to them and just asked, hey, what are your problems day to day? What would you pay money to solve? And luckily, one of these people we talked to was a director of security, and he started complaining about his guards, sort of how unreliable night shift work can be, why his cameras weren't enough. And we kind of, the first thing we said is, can we build these smart security cameras? And he actually said, no, like I already have smart security cameras. But someone comes in wearing a hat and you can't see their face. It doesn't matter how smart the camera is. You either can do nothing or you can call the police. And that's why people still have guards. They still have guards to follow up and investigate as something's is happening, and understand and collect more information. And that's when we realized, hey, this is the perfect job for a mobile robot. It's kind of that blend between a guard and a smart camera, where it's not just about detecting a person. It's about, once you detect them, being able to follow up and gather more information and go up to the person and say, hey, how can I help you? And then you can make the call of,
what
do I need to escalate this or not? Exactly. It's kind of like this, you need this third option of following up and getting more information before making a final decision. And so actually now that's a big direction that our product is going, is that everyone now has tons of smart cameras and smart sensors. And all of these smart devices for enterprise security create work. They create alerts. They create alarms.
Yeah.
And actually, a lot of our customers that we've talked to have had to hire more security guards because they have all these things.
That's funny.
Because they need to go investigate them. They need to go deal with false positives. And our strategy is that all of this other security infrastructure is creating alarms, and our robots are actually reducing work.
Yeah.
And the robot automatically gets dispatched to go investigate these things and say, hey, this door force alarm was actually a false positive. The door looks fine. And then it gets dispatched to the next alarm. And so basically, there's kind of these two sides of security. There's the detection, and then there's the resolving. And we actually want to be much more on the resolving side. So the robot is not just a moving security camera. It's much more than that. It's the ability to follow up and resolve things, which is what a guard does, not what a camera does.
Interesting. I feel like you said a lot of very interesting things just now.
No, thanks. Yeah, it's a really fascinating space, I think, and it's very cool seeing how more people in enterprise security are building sort of these. They're trying to build these much more autonomous systems, and these much more sort of systems for handling physical security without needing a lot of human input. But also, one of our customers quoted General Patton to us and said, "Fixed infrastructure is a monument to man's stupidity." It's a quote from World War II, and this is sort of why no one builds castles and fortresses anymore, is that any fixed infrastructure you have, anything that's static, is at some point either going to be broken and not replaced, or someone's going to find a way around it. And that's the difference between cameras and sort of fixed sensors and robots and guards, is that we're infinitely adaptable. A customer can call us one day and say, hey, our left door alarm broke. Can you change the robot's patrol to stay in that area? And we're like, yep, we can do that. Just like a guard, you can just call us and we'll immediately respond to whatever that is. And that's why we don't want the customer to need to go in through some interface. We don't want Cobalt to be a static system. We want it to be a flexible and responsive system. Because that's why they have guards.
I'm seeing, so the way that I'm thinking of Cobalt now is you guys are almost like you guys are a security company, and your personnel is your robots.
Exactly.
Which is very interesting. It's an interesting model. It's almost like, I don't know, you've taken all... It's interesting because you're not selling the robot, which is what I first thought it was. You're selling the service around the robot.
Exactly, yeah.
And
I think that's, as we scale, we're exploring sort of splitting that off so Cobalt can stay more of a technology company and work with guard partners.
What do you mean?
That would then provide the operators.
Is splitting exactly what off?
Work with an outside partner for sort of those
the security
to be the
part.
Operators to be the security part. So Cobalt can stay more of a technology company.
I see.
But I think at the beginning, it's a really, really good strategy for us to be very...
I see seems to trigger Siri when I say see.
No, that's...
Sorry, what did you say?
That basically, there's this balance of us being a technology company and us being a security company. And at the beginning, it's really powerful that we can be both of those things.
Yes, because you can do that.
Because we get vertical integration. And that means that, our engineers are sitting alongside our security operators and seeing what the deficiencies of the robot are and seeing what the pain points are of the customers. And they're talking to security end users. And if we were just selling the robots and then someone else was implementing security with them, we wouldn't get any of those learnings. And so we want to be a place where we are a technology company, but that's very, very integrated with the security and very product focused and really sort of end user focused.
Gotcha. That is very interesting. Yeah, I initially, all the questions about configuration and things, I was assuming that you just sell your robot, they buy it, the customer buys it, and then they figure out how to use it in their space. When really you're saying, okay, our robot is going to be like an employee, and every time you want to update it, you call us, we make the changes, and then you present them. So you present their security manager or something like this with the data, or whoever's relevant with the data that the robot captures, this kind of thing?
Yeah, exactly. And that's sort of the way that we provide the end service. The service isn't the robot. It's the data that we collect and provide to them. And there's a couple ways we do that. One is, if there's ever any urgent incident, we just call them.
Yep.
And then the customers have a interface on a web dashboard where they can live see what the robot is seeing.
Yep.
And they can dispatch the robot to go see something. So we might call them and say, hey, there's a break-in in progress at this office. Pull up the dashboard and you can watch while we resolve it. And we've actually we've stopped a few break-ins.
Wow. Congrats.
Actually, thank you. It's actually much more boring than you would think. Modern
you just go walk up to them and you're like, stop, and then they're like, oh no, and then they run out.
Modern criminals are not in ski masks, breaking into windows. They are social engineering their ways into office buildings. And so,
what do you mean social engineering? What is that?
They're pretending to be an employee that forgot their badge, but they're actually not. They're well dressed. They're trying to blend in. They're trying to blend in around other people, and sort of. So we had a customer where one of their door locks stopped working, and a door swung open to the streets of San Francisco. And fairly soon after that, our robot detected a person in the site. We approached them because our operators didn't recognize the person, and we video chat and said, hey, excuse me, can I see your badge? And the person was immediately like, oh, I'm lost. Like, I didn't know I wasn't supposed to be here.
That's funny.
It's like, it's 2 a.m. in an office building. Sure.
Yeah, you just happen to be here. Yeah.
We called the customer and called the police and then escorted the person out the door. And then the robot was able to stay sentry at that door that was open for the rest of the night.
Wow.
And so that's the kind of flexibility and responsiveness that we want, is that as an emergency happens, we don't want to just be on a fixed rail like a camera.
Yeah.
We're going to be doing what a guard would be doing. And that's, making value calls as we go and deciding what is the best way we can provide value to this customer.
So how do you code in all that behavior and the flexibility? I'm imagining like something like behavior trees or whatever they do in video games, where it's like you can have fairly complex layered behavior where I try this and then that doesn't work, so I'm going to try this other thing, and you can keep moving from limb to limb of the tree. How do you encode your behavior, basically?
Yeah, so that's a really good question. We use hierarchical state machines for most of our behaviors, but actually I'd say a layer above that, and I think that it would be misleading to say that our state machines resolve that case. We keep our high-level decision-making done by our human operators, and so they are able to, on the fly, say, hey, don't patrol tonight, stay sentry here. And basically giving them, think of it for our operators, it's more like them playing StarCraft. They can tell the robot what to do, and we provide a really good interface for them to be able to tell the robot to do different things. Okay. And that might be go patrol this floor, that might be stay here, that might be go recharge. And that high-level decision-making we want to be made by our human operators who are very highly trained and know our customers. And then our state machines that we build are basically these primitives for the robot to be able to do these block-sized actions. But it's the human that's deciding sort of which of these should be done.
Interesting. So the human at a very high level, it's almost like picking the mode of whatever the robot will do. It's like a delegation, effectively.
Exactly. Yeah.
And then the robot will go and it will execute this this decided behavior, and you have all those primitives, those smaller action control loop things. So go around this desk, go look in the unexplored territory, these kinds of things.
Exactly. Yep. Yep.
Interesting.
Yeah, and so we want to build the system, and I think it's we really consider our system. It's the combination of the
human
robot
and
the human operators. Yeah, and that's really it's those put together that allow us to provide a great service for our customers. Because I think we've seen self-driving cars being worked on for 10 years now, and they're just barely starting to actually give get out into the market and give taxi rides to people. And for us, what really attracted me and my co-founder to this idea was that we could use this combination of humans and robots to immediately get into the market and start providing value.
Like right away. Yeah.
Right away. Huh. Even though pieces of the robotic technology weren't there yet. And now, as all this technology gets better, what it does is it increases our ratio of how many robots each one of our operators can manage.
Gotcha. So tell me a bit more about the human in the loop kind of thing. So how does that work? They're on a computer somewhere, logged into some web application that you have, or like how does it work?
Yeah. Great question. So we have a lot of operators, and they work from our offices or our satellite offices, and they have a sort of this big 3-monitor setup, each of them and basically they can zoom into one robot, and they have a fleet management view, and they have sort of a communications view. And so they are
fleet management. Sort of so a little bit slower for that. So fleet management, if they're using many robots in the same environment, or
exactly. So they're looking at sort of the health of all of their robots.
Okay.
And sort of how we have it work is there's 5 to 10 of them on shift at a time, and they have split up the fleet of robots of who is responsible for which robots. Plus some overlap and sort of dynamic changes. And they're saying, hey, I'm watching my robots, and the robots are telling them, hey, I think I saw something, or hey, I need help, I got stuck.
Yep.
And they are zooming into these robots kind of one at a time as events are popping up that they need to go resolve.
Interesting.
And so then they switch to that robot-specific view and can go take action, whether that's video chatting with a person to talk to them or ask to see their security badge, or maybe it's changing the patrol route to go around a new obstacle or something that's causing issues for the robot. And then if anything is needed, they can go communicate with a customer. They can escalate something that the robot sees into the customer's dashboard so that they can see it.
So they have their setup where they see many robots. They have a view into one robot. And then maybe they have a good way of accessing commands or something for escalating the situation. Is this one robot specific, I guess? Or is it, I guess you don't have multiple robots coordinating, or maybe you do. I don't know.
Yeah, so for most of our customer sites, there's one or just a few robots. But individual customers have many robots across their different buildings.
Yep.
And that's one of the other things we really see is that a customer that has us one place really likes to expand to all of their different offices and satellite offices, so that they can get this consistent data and reporting evenly across sort of their whole site or their whole collection of sites. And so they, there might be a call tree that applies for these 10 robots that are all from the same customer.
Gotcha. Interesting. Okay.
Yeah.
And then, so when the robot is stuck or anything, the person takes over, gives them high-level guidance. Do you have to do anything where the person will do... So you mentioned, like, pick another route or something like this. They won't do, like, map editing or something. Like, will they correct any sensor errors or say this region is actually a spot you shouldn't go?
They have some annotations that they can add like that on the fly. But if there's anything bigger, like if they come in one night and realize that the customer has totally rearranged their furniture, they can create a ticket for us to go and remap that site. And we can do all of that remotely. And it's kind of like the next day, we would go look and see what edits.
So you're working within existing maps. It makes sense for this kind of thing. So you can localize.
And that's something where when we first go to a new customer, that sales engineer goes on site for a day with the robot, shows it the building, shows it the elevators, shows it any sort of doors or handicap buttons it needs to know about, and then we have that map that we can navigate against.
Is it some?
And we're using right now some pretty we're using ROS, and we're using a heavily modified version of Move Base and the nav stack and AMCL. So a lot of the kind of the standard but improved ROS systems.
Yep. So you forked specific things and have improved them internally.
Exactly. Yeah.
Which ROS are you using? Are you using ROS 1 or are you using ROS 2?
Yeah. So we're using ROS 1. We haven't yet seen a lot of other people switch to ROS 2 for sort of live deploy to customer sites applications yet. We're seeing a lot of interesting traction there and sort of new things getting started with ROS 2. But we haven't yet seen
all of the
seen sort of the level of deployment that we'd like to see before we make a move.
Gotcha. How has it been working with the ROS stack for you? Like, what are your I don't know, just what are your impressions of it? And
I really like ROS. I think the general messaging architecture is a really, really good way to design systems, and it sort of enforces that microservices architecture in the robot, and really good separation of concerns.
Definitely.
To be able to work on a lot of different pieces and just know what the interfaces are. So I really love ROS conceptually. There's a couple downsides, and there's a couple rough edges, especially of ROS-Pi, the Python implementation. But the things that we work around, and I think, what I love most is just the community and the ecosystem. That any sensor we find, it's like, oh, there's a ROS node already made for it. Like we can just install it and we're ready to go. And I really love that. And I want to find more things in the future where Cobalt can contribute back into open source. And I think that's something that I want to do as we get more libraries and things built that might be a little more general to people outside of just us.
So for your fork of Nav2 or any of these other libraries that are built on top of ROS, what was the decision? Are they public, or what was the decision to fork for this kind of thing?
Yeah, they're not public yet, but it's something we've thought about. I'd say two of the major areas there that we've edited is one, kind of just overhauling a lot of the innards of Move Base to make things more reliable.
I don't know Move Base very well.
So Move Base is one of the big packages in the ROS nav stack that's responsible for getting a robot from point A to point B. And it's kind of the nice high-level interface where you can say, hey, send a nav goal here, and Move Base is a open source ROS package that implements how to do that.
Gotcha.
And you give it some configurations about where to find your map, where to find your cost map and sensors to not hit obstacles, and how to talk to your motors, and then it can go. So that's kind of the starting point of what we've very heavily modified. One of the interesting things that we've had to change it actually is the ability to send intermediate goals. So we,
as opposed to just the actions abstraction?
As opposed to we send an action that has two goals. Sort of the final goal and a waypoint along it. And it will actually start moving towards the waypoint even if we can't reach the final goal.
Now, why is that better than just sending two actions? So an action to be, give some background for those who are not familiar. So you send something, it's a high-level thing that you'd like the robot to do, and then it will send feedback throughout the time that it's completing it, which you can do something with. So you could say, oh, cancel, never mind, or just monitor it in some way. But why is the two actions within one action, why is that different than just sending one action and then another action? I guess it takes both into account?
It's lower latency. And what we care about here, and the motivation for this, was actually getting into elevators quickly. A lot of times when you press the button at the outside of elevators, you have 3 seconds until the door starts closing. And if it's across the elevator lobby, we actually have to move pretty fast to get in there. And one of the things that we've seen is that if you send just one ROS action and so basically one of the things here is that if the elevator door has not yet opened, if you send a nav goal into the elevator, it will sit there and wait until the door opens and then start moving because it can't plan a path there. And so basically what we wanted to do is, hey, we're trying to get into that elevator, even though the door hasn't opened yet, we should start moving and at least get lined up in front of it. And basically doing both of these sort of within MoveBase lets us seamlessly transition into that second goal as the door opens really quickly, rather than stopping and lining up with that intermediate goal and then sending a second action to go inside. It's much faster for us to actually switch that goal without even stopping the robot.
Yep.
As soon as it sees that the second goal is viable, it switches over, and the local controller just keeps on going. I'll also note for any listeners that aren't familiar, MoveBase and the nav stack sort of is a two-level system. There's a global planner that is sort of like, think about it as your A-star, your Google Maps of, I'm here, I'm trying to get there, plot a route around my obstacles that I know about and get there. And then the local controller takes in that path and is simulating its wheel trajectories to figure out how it should follow that path most quickly to get to that point.
Okay. And then the interest in eventually open sourcing things. So from the company perspective, it's not quite your interest to maintain a like an open source library or anything. But why do you feel like you'd like to open source things? I mean, I'm at an open source company, so clearly I like it. But
I think for me, it's a sense of giving back and like paying it forward. Cobalt was very heavily dependent on open source at the beginning. We actually launched our first product and deployed to customer sites with myself and a single other robotics engineer.
Wow!
And we would not have been able to do that. And plus some web engineers and hardware. But we would not have been able to do that without really heavily standing on the shoulders of giants and using these open source packages and building layers on top of them. And I just found that really exciting that, two people were able to build a production ready robotic system by using a lot of these open source packages. And I just really, really enjoy that. And I think I want to make sure that, problems that we solve just sort of for humanity. I don't want, engineers everywhere to need to, solve the same problem over and over again.
I love it.
Now, of course, a lot of the things that we built are very sort of,
specific,
customized to our robot, but, we're always looking for things that could be a good thing to open source.
Now, so 2 people, you had a production ready robot. How large are you guys now?
We're about 115 people right now.
And so that's a lot of the people that are doing the security related things.
Exactly. Yeah. About half of that is actually our human operators that supervise the robots and control the robots. Our engineering team is still very small. It's about 23 people.
Wow.
And that's split, again, across robotics, web, and hardware. So it's a really great place where, the teams are very small. Each person can have a really big impact and solve a lot of interesting problems and have really good ownership over the code.
Totally. So going from 2, you had a production ready robot. Now you have 20 engineers or so. What are the additional 20-ish people, like you said, or what are the additional 18 people or so doing?
Yeah. We had 2 engineers to get to the point where we could have 1 or 2 robots rolling around. Now with a much bigger fleet, there's all sorts of other, other things we have going on. And also for those first production ready robots, that means that we had 1 operator at the time. And so if he's only looking at 2 or 3 robots, the robots can be a lot more needy. And so really now everything is about scalability and saying how many robots can each one of our operators handle. And that means the robots being able to, not get stuck as frequently, being able to unstick themselves if they do get stuck in a navigation area. Building a lot more features out for our customers, better data reporting, better information that we can send them, and do that more reliably and more quickly. So I'd say it's really about adding a lot of meat to the bones of what our product service is, and increasing reliability and making these robots really rock solid so that we can scale out the fleet.
Yeah. Can you tell me a little bit about manufacturing your robot, or just in general making them and deploying? Because you have how many robots out in the world now?
We have over 100 robots deployed.
Very exciting.
So we actually manufacture all of our own robots in-house. In our right now our office in San Mateo, in the Bay Area of California. And so we've really liked having manufacturing in-house because it lets us have a very, very fast iteration cycle. between engineering and hardware. And so we can solve issues as they come up and roll them back into the design and have engineering right there to solve any issues that happen. And so now as we're scaling up manufacturing, everything is getting a lot more locked down. And as volume is going up, you start to see 1%, 1% errors where if you're buying, SSDs, it's a 1% chance that they come out of the box dead or something.
Yep.
I don't know about that particular component, but
some
when you're
arbitrary
building 10
component,
robots,
some widget.
Yeah. A widget, when you're building 5 or 10 robots, you don't really need to care about that. But when you're building a lot of robots, you're going to have anything that can fail
Will fail.
Exactly. And so that means you need to build in a lot more, basically unit tests for each component that goes into the robot. Everything gets tested before it gets put in. They get put into subassemblies. Those subassemblies get tested before they get put in. And trying to catch any of these errors sort of as early as possible.
Mm-hmm.
And then every robot that gets finished goes through 2 days of battle testing at our office before
I like
it goes
that you
to
call
a
it battle
customer site.
testing.
Yes, exactly. And so it's basically the robot goes back and forth across like a simulated office environment with very rough and bumpy floors for 2 days to try to shake itself apart. And it goes through basically making sure that it can do all the different kinds of tasks that it will be required to do at the customer site. So we can catch any errors or manufacturing defects before it gets shipped to a customer.
Mm-hmm. How is it? So you're doing your assembly in-house. I assume you're buying a good number of components to put together?
Exactly. Yeah.
How has it been sourcing those components? Like the process of doing that is very interesting to me.
This has been a very challenging year with the global chip shortage.
I bet.
And so, a lot of the components are either off-the-shelf sensors or compute pieces, and we do design our own custom PCBs that go into the robot.
Mm-hmm.
And I'd say that most of the off-the-shelf pieces, it's fairly easy. We do research online, we test different components, and make sure we go with vendors that are sort of more industrial, where they say, hey, we're going to guarantee that we're going to keep making this part for at least another 3 or 4 years.
Oh, interesting.
There are, in the early days, there were more consumer components in the robot, and things like that are dangerous. And, it works great, but, the next year it's not available on Amazon. And, in the first version of our robot, there were definitely a couple components, purchased off Amazon. And it's a great supplier until they disappear.
Yeah, gosh.
Yeah.
That's so funny.
Yeah. And now with the chip shortage, one of the big challenges has been that, so many people are ramping up production for different things that even very simple components like inductors that go on a PCB will go out of stock. And there's been a couple times where if you don't have those stockpiled, you have to change a PCB design to use a different part or a different value because you can't buy
it. Oh, wow.
Whatever component that goes on it. And so things like STM microcontrollers are very hard to come by now, and even some passives are, can be difficult to find.
Gotcha. Passives like resistors.
Exactly, resistors, capacitors, inductors. Yeah.
Wow, that's really interesting.
So it's been a really crazy year for supply chain management and inventory, but we've done a good job, and there's been a lot of heroic lifts from the engineering team here to
redesign things with available
find
components.
Things, redesign components around, redesign boards around what's missing, and find other options.
Mm-hmm. Let's see. Now, another thing I'd like to talk about, the human-robot interaction of your robot.
Yeah.
So it's covered in fabric. Just tell me some of your human-robot interaction considerations in designing the Cobalt robot.
Absolutely. So this was one of our really, really big sort of goals when we started this. Because when we, again, going back to kind of that customer-driven approach that we wanted to take, when we first talked to customers about, whether they would like this product, whether they wouldn't, a lot of their biggest fear wasn't that the robot wouldn't work. It was that their employees would be scared of the robot and that they wouldn't like something like this. And so we put a lot of effort into trying to dispel that fear and making the robot as friendly as possible. And so that's why we actually contracted a design firm that's very well known called the Fuse Project. and worked with a world famous designer named Yves Bahar. He actually helped design the Herman Miller office chairs. And kind of the sense that we wanted to go for was not Terminator or RoboCop, but we wanted to feel like a high-end piece of furniture. That's something that's natural to be in the office, that's helpful and useful, but isn't as much of like a intelligent thing that you're going to fight with. And so that's why we went with sort of the fabric base, is that it's nice and soft, and it's actually, we've seen it like crazy. It's we go when we went to early customers and we do an onboarding for them to bring the robots there and basically tell the employees what it was and how it was going to work. A lot of people were initially very scared about the idea of a security robot. They were picturing Terminator or RoboCop with a taser, but as soon as they came to the all hands or the lunch and learn that we would host, and they saw the robot and they touched the robot and realized that it was soft, and they talked to one of our operators, they realized, oh, this is just like a security guard that just happens to be remote, and that just getting people to come touch the robot and interact with the robot. And see what it is really, really helps with that. But Hollywood sort of Hollywood's depiction of robots is definitely not good for us, and we're trying to stay far away from that.
Very interesting. That's crazy to me that people were afraid. I mean, I guess I've been involved in robotics for so long and not talking to customers. So then
exactly, and this is something that's challenging, and that why we wanted to make sure that we were very close to customers is that for us as roboticists, it's very easy to say, oh, who doesn't love robots? And it turns out a lot of people don't, and so it's something that we want to be just really, really careful of, and really just take very good consideration of. And so actually that goes in not just to the industrial design of the robot, but also into a lot of what we call the body language of the robot. And the software and behaviors. And so there's some interesting things there. We'd have an issue in the past where if the robot got stuck and was waiting for a human operator to help it proceed, if it was stuck near a person, the person would think, why did the robot stop and just stare at me for 10 seconds, and then continue on? And actually, it was that the robot was just stuck. It wasn't staring at them. It just happened to get stuck near them.
We assumed intention.
But a person that doesn't know that assumes there's attention. So now we do things like if the robot gets stuck, it's something displays on the screen that says, oops, I've gotten stuck. I'll be on my way shortly. And make sure that people understand what the intention of the robot is. And that's made people a lot more comfortable around it.
What other... So that's really funny about the body language of phrasing it as the body language of the robot. And so I see, so you'll see someone who's watching the robot or sees the robot come up, and they assume a sort of intention behind whatever the robot's doing. And so then you have to, so you're making this explicit message of, oops, I'm actually stuck. I'm not just like staring at you or something like this. How do you find those? Is it case by case? Where someone will be like, this made me uncomfortable of what the robot did? Or how do you go about designing robot body language? And I would love to hear other examples of robot body language.
So I think one of the best ways that we do it is that we have our own offices patrolled by Cobalt robots for our security. And so that just means, we're dog fooding. We're trying our own product. And dog fooding, for anyone that hasn't heard of it, is a term of basically, if you're a company that makes dog food, you should eat your own dog food to make sure it actually tastes good and is high quality.
That's hilarious.
And
what a great
don't
expression.
Use your own product, if you don't use your own product, like how can you expect customers to use it? So that's something that's really important to us. And so that as we're working in the office, to feel what it's like to have a robot go past you, or someone to come up and ask to see your badge with the robot. And so doing that is really, really important, just to get that sense of what it's like. We also have engineers that will go on site to customers, with customers, and walk around with the robot and see how people interact with it. And we just really try to get as much exposure as possible for our engineers to be with end customers and also to be with our operators. Because a lot of times our operators they're seeing everything that goes on around the robot, and they're talking to people, and sort of they'll hear complaints, or they'll hear sort of people being delighted that they're talking to someone through a robot. And we're just trying to keep engineers not just looking at code, but involved with the end product and seeing the pain points is really important to us.
That's very interesting. Have you, so there's a growing space of research, the human interaction space. Has any of that research been useful to you guys, or like have you been leveraging it, or it's all things that you've been finding kind of organically?
I'd say it's a mix. And one of our advisors, Leila Takayama, she's an expert in HRI. And so we brainstormed with her. And I'd say that's a mix of things that there's a lot of things that once you hear them feel like common sense.
Mm-hmm.
But there's also really good things that are, very not intuitive that are very cool. One of the things that we had heard and had learned from HRI experts and some of this research is that being completely stationary for humans is actually a very aggressive and sort of assertive behavior. It's like,
menacing.
I am rock solid and menacing. And for a robot, though, because like by default, a human doesn't stay stock still, they fidget.
Yep.
And a robot by default stays stock still. And so one of the ideas that we've had is that if the robot is idle, instead of being stocked still, it should fidget. It should maybe turn back and forth a little bit. That's one of the things we're thinking about implementing now. But kind of going back to that body language is that being stationary is actually like more aggressive than moving sometimes. And so there's a lot of interesting things like that that we've learned about.
Interesting. Let's see. So
and I think those are often called keep alive movements.
Keep
that
alive.
Basically show that the robots.
Yeah.
Show that the robot is still active. It's still doing something, even if it can't make progress towards its goal.
Yep. Yeah, I'm always a little disappointed as someone working on robots that almost all the time our robots are off. And so it's like almost all of the robots are just completely still for almost all the time I'm around robots, which, I don't know, maybe it will change at some point in the nearest future.
Yeah. And I think for us, that's actually an interesting segue that some of our future plans is making our robots a lot more general purpose. And our thoughts there is that security guards actually do a lot at employers. They're making sure nothing bad happens at night. But during the day, they're doing visitor management. They're checking people in. A lot of times, they're almost acting like a secretary or sort of a receptionist. And so one of our goals is that while the robots are doing security at night, during the day, they can be a virtual receptionist and check someone in just like Envoy, but then actually lead the person to the conference room, where they're supposed to be. And the idea is that, once you have a robot on site somewhere,
might as well use it the whole time.
Any new functionality that you can do are software updates. You have the hardware there. It's already paid for by security because that's sort of the big cost, and you can start adding all these other applications. And we've already started doing that with some of that facilities monitoring that I talked about. But one of the next ones we're looking at is more daytime applications
to
keep
exciting.
These robots, more active, and so people will be able to see them moving around and interact with them during the day.
Mm-hmm. Let's see, maybe a bit more of a controversial question, but so how does this relate to jobs for security guards and things like this? Because it is, in a sense, automating the job, and maybe in the end, automating receptionists or inspection people. How do you look at this?
Yeah, that's a really good question, and definitely one that we take very seriously. What we found is actually that robots replace tasks, not jobs, and really sort of change how jobs are done. And what we've seen is, we've never had a security guard laid off because of a customer getting robots. What we typically see is that customers can't find enough security guards that want to work night shift. Or they'll work night shift, but as soon as they have any other job opportunity, they're switching to something else.
Interesting.
Exactly. And so we deploy with customers, and they can take their good night shift guards and let them work day shift now. Or have the guards focus on more interesting things, like interacting with people, while the robot is doing the much more monotonous sort of patrolling around, going and checking on these alarms and checking for doors and windows being closed. So it's really sort of changed how people do security. And the other thing is that customers are adding these in places where they didn't previously have guards. Because guards are quite expensive, especially if you want to guard 24/7, 365. It can be very expensive. You can actually need 3 or 4 security guards to cover that amount of time.
Yeah.
And so what we see is that companies had guards or receptionists at their main office, but none of their satellite offices. And now, because the robots are much cheaper, they can put the robot at all these satellite offices where they never had security presence before. and basically get that additional coverage.
Gotcha. That's awesome. I really like framing it in the robots replace tasks, not jobs way. And I'm hearing this pattern in the last several interviews that I've done, where it's like it's the same thing you're saying, which is they were having trouble finding the workers for this kind of thing. Um, so like I'm thinking of the interview I did with Melanie Wise, who in factory settings, like there's a tremendous shortage of workers. And so it's interesting to hear the same kind of thing here, that there's a shortage of security guards.
Yep, exactly. Yeah, and it I think comes from the fact that robots and humans are just good at such different things. Humans are amazing at making good decisions, handling nuance, interacting with people, and they're terrible at anything monotonous or something that requires long focus. And a robot has no trouble at all for 8 hours, never blinking,
Yep.
and going and checking whether that door is open with just as much sort of sincerity and carefulness as the 100th time they did it as the first time they did it. And so it's something where you can create a much better solution using both of those, and that's it's at several levels. That's why we have our human operators that are handling the interesting parts of security while the robots are doing the monotonous parts. And we've seen the same thing with our customers, is they can take the monotonous parts of their security program and do them with robots and redesignate their security guards to be working during the day shift, much more around people responding to things.
Gotcha. I'm hearing another echo in this interview where it's that we have humans in the loop in some way, augmenting the tasks. And you've spoken about how the humans are doing the things humans are good at and the robots are doing things that the robots are good at. So long attention, grueling, mundane work. Can you just talk about this model within robotics a little bit? Because I think it's a big one. And it seems like we're at a good time for this.
Yeah, absolutely. So human in the loop is definitely a really, really big wave in robotics and I think this kind of comes back to my point that it's let us get into the market and ship a product when in an area where the robotic technology was not good enough by itself to do the whole job. But because we're able to kind of augment these two things together of what the human's good at, what the robot's good at, we can provide the value from day one. And it lets us both focus the engineering work on the pieces that are easy for robots and save, it'll be very hard to automate something like how do you respond to a person that says they're an employee but doesn't have their badge? Like that's a crazy hard situation to need to handle. And, it would take engineers a lot of time to write something that is correct and
if there is a correct, because it's case by case.
And there isn't a correct. It depends probably for each customer how they would want to do it.
Yep.
And some would say, oh, just don't let them in. Some would say, call this number and verify whether they're there. And that's something that having a human do that, they can respond with a lot more nuance. And I'd say there's a couple different archetypes of human in the loop. Of sort of different levels of shared autonomy. And we use a couple of these different levels. I'd say on one extreme, there's just sort of complete autonomy. And that, you can see with factory robots where a person doesn't need to be involved at all. On the other extreme, you have complete teleop. It's a person directly controlling a robot, one for one and exactly specifying what it should do. And a couple of the layers in between, there is back to the sort of the autonomy side, there's autonomy with supervision. So the robot is still doing an autonomous thing, but a person is supervising it, and they can hit the stop button or they can hit the correct button. One more step towards human is sort of human review, which is the robot is explicitly saying, hey, I'm about to make this decision. Can you approve it? And that's great for something like, hey, I am, 90% sure this door is open. Can you approve this? And that's great for things that are, something where we want to remove false positives. We don't want to inundate our customers with false positives of this door was left open or, we saw this person. So anything like that, we always go through human review first. And it's something the robot can do by itself, but we want to make sure a human reviews it. Then kind of one step more towards human, I would say there is, I don't actually have a great term for this, maybe robot accelerated or robot assisted human decisions.
Okay.
And what that might mean is, let's say we don't have any software to check maybe a new customer feature, go check whether all of our fire extinguishers are there. Maybe we don't have code for that yet to classify whether we see a fire extinguisher in the correct spot.
Mm-hmm.
The robot could still go and collect all the pictures of the 10 places they're supposed to be and then show the human them all at once.
Yeah, so you can
and
batch.
so that way the human can batch their work,
Mm-hmm.
and we don't actually have to automate the work. We just have to automate walking between the work.
Yeah.
Where a security guard would take 45 minutes to go walk around and check all of these fire extinguishers, the robot can do that 45 minutes of walking, and then our human operator can go review them in 30 seconds. So basically, batching and assisting work to let a human give just a little bit of input that makes the work, basically it's automating 95% of a task
Mm-hmm.
and letting the human do it. And then kind of we get back, that's sort of the far end, and then maybe you just have complete human control
Mm-hmm.
on the other end. So we have things that are sort of all along this spectrum. And as we automate more things, we try to move things further to the right to make them more automated and take less human time.
Mm-hmm.
And that's a lot of the interesting things that our engineering team is working on now is, hey, how can we take something that right now we're just showing a person, and how can we have the robot make a decision and just have the human review it instead?
Yeah.
Because that's a lot easier.
For sure.
And the really cool thing about this model of having these different collections of kinds of human in the loop
Mm-hmm.
is that our humans basically act as a buffer for our engineering work. Where if there's a new feature that a customer requests,
Oh,
we can
that's
start
really
off
cool.
where it's done fully manually. And what that does is there can be a crazy new request from a customer. And normally, you'd have to say, do we do this? It's this big product decision.
You can try it and then see if you can automate
we can
it.
try it and see if they actually use it, and see if other people actually like it.
Yep.
And then if everyone does start using this feature, great, let's automate it.
Wow.
But if no one is using it, if it's kind of a one-off, you can either leave it manual or quietly deprecate it. So it lets us kind of dip our toes in the water with a lot of features, and then automate them as needed later. So we spend a lot less time implementing features that no one needs, and a lot more time implementing a feature once we have amazing training data for it and examples.
Yes.
Because then when we go and do want to automate it, we have 2 months of humans doing it manually with all of that data recorded.
Yeah. Huh. So for many of the things that you're inspecting and where you get the data and then you try to do it in an automatic way, are you using any machine learning on this, or what kind of tasks are you using machine learning for?
Yeah, so we use a combination of classical methods and machine learning for a lot of these different things that we're inspecting or checking.
Mm-hmm.
And kind of one of the ways that we refer to this is auditing the physical world for our customers.
Auditing the
so
physical world.
Yeah, exactly. You want to be able to audit that everyone in your organization has, two-factor authentication turned on. The robot lets you audit the physical world in a very reliable and trustable way. That, before you couldn't really trust, your guard says, yeah, all the doors are closed. And we've had plenty of times where someone says that, and then we send the robot and check, and there's two doors propped open.
Your robot
so
is that
this
employee that's really diligent that some of the other workers really dislike. Like, humph!
Well,
I said it was done. But
humans are not exactly. Humans aren't good at that kind of diligence.
Totally.
Work, but robots are. But so basically, sorry, what was your question again?
What do you do with what is machine learning? On your platform? What kinds of tasks are you learning?
So generally, I would say that machine learning should be a last approach when.
It's just you said training data,
fail.
I lumped it. I associate it with it. I know you don't. You can use classical methods with the training data to just see if it kind of lines up. But
yeah, exactly.
Mm-hmm.
So I would say we usually start for something new that we're doing, trying to use classical methods and trying to look, hey, can we write an explicit solution for this? And then if not, if it's something that's challenging, we'll train a neural network, based on some of the data. But it's actually really interesting that we've gotten very far using some even classical computer vision techniques of looking for diffs.
Really?
So an example is because our robot has very good localization, we can go take a picture of the same thing from exactly the same spot each time. And we can just look at a diff and, hey, this looks different than last time. And then suddenly you have a way to inspect, anything new, even if it's
whatever the arbitrary scene is. Yeah.
Whatever the arbitrary scene is, we have now a way to flag this up to an operator of, hey, I don't know whether there's a fire extinguisher here or not, but it looks different than the last time I saw it. And that actually lets us
There's no semantic understanding, but you're still like, I ran a diff on the old image and the new image. Where I looked at the difference and I saw that there was this many pixels different or some measure of entropy or whatever it might be.
And we found some very interesting pre-processing techniques to do the diff in a non-pixel space that lets us
in a signal space.
It's much more invariant to lighting conditions and things like that.
That's awesome. Can you speak on that a little bit, or is it?
Yeah. One example is that you can do things like edge detect the image and then do diffs of the edge detected images. And that lets you see that something sort of with hard outlines has moved in the scene, but an overall lighting change is
not very picked up.
Doesn't trigger that. And so we have sort of things like that that we can do to very easly notice changes.
It's cool to use these incredibly simple operations. So if you want to get an edge detection, you just multiply a +1 and a -1 over convolve it over the whole image, and then you get your edges from the resulting image. It's so crazy that you can use that, and that will be useful and fairly invariant, which is very nice to different lighting conditions. And
we're really big fans of keeping things very simple in the design, and if something feels sort of overly complicated, it's probably going to be fragile when it actually gets working in the real world. We see lots of things, from research, did they need to do that? Like that's, or was that something in a research paper just to make it more publishable?
Totally. How funny. Now, so we're running out of time. I'd like to talk a little bit. So your experience in startups, in this startup, and you said you previously were starting companies or have started companies. Talk to me just a little bit about this time, like right now, for being a robotics startup, and maybe just the landscape as you see it.
So it's a really interesting time for robotics companies, and maybe I'll actually kind of back up to maybe kind of my history of how I got here. Is I started my first company called Posmetrics in college with a friend. We dropped out of Harvard for a year, went through Y Combinator, and that company eventually got acquired.
Wow.
I went back to school to finish my degree.
Oh, congrats.
It was a really great
awesome.
experience. Thank you. That's actually where I met my current co-founder, Travis Dial. He also had a startup at the time that he was working on. We became pretty good friends chatting about robotics, even though neither of us at the time were doing robotics. And we just kind of stayed in touch, and we're always bouncing startup ideas off of each other. And I think the really cool thing of being a second-time founder was it just felt like we knew what we should be doing. Looking back to the first startup, it's crazy that we got anywhere because we didn't know what we were doing. It's like, oh, maybe we should try marketing today. Maybe we should try building new features. We didn't know what the goalposts were. And I think that's the really great the really great thing about doing something the second time is we know what are the goals that we need to hit. And I think that a lot of the ways that I think about startups is progressive de-risking and look at what are the experiments you can be running each week that reduce the risk of your business as much as possible. And think about what is that next milestone we need to hit and what are the kind of waterfall things that we need to do to get there. And a lot of times for early stage startups, that's different funding rounds and sort of think, okay, well, to get this, I need to probably have this much revenue. That means I need to get this many customers. That means I need to get this many features built. And so you can kind of work backwards to what you need, and that helps decide what you actually need to be focused on as a founder, what you need your engineering team to be focused on, to decide, really what's going to be a feature that works and is important and, helps the company versus something that's just nice to have.
So can you speak a bit more about picking a problem?
Yeah, sure. So when Travis and I started looking at ideas, we had a couple constraints. we wanted to find something that we could see ourselves loving and doing for 10 years. And, Cobalt is an amazing fit for that.
Hell yeah.
Security just feels like this amazing first use for robots and this really good opportunity to get robots out into the physical world and get around people, not just in factories where no one's going to see them, but in office buildings where they're going to be around people all day. And it was something that could be done with today's technology sort of immediately. The other sort of constraint that we had we wanted to find something that we could immediately get into market with, no research and development. And that was another really good thing about Cobalt is we could go and we could use human in the loop to fill in the deficiencies. And we didn't want to do something that would take, a lot of R&D or would have very high technical risk.
Yep.
We wanted to find something where we could use today's technology and that it would just get better over time. And then our last constraint, believe it or not, was no hardware, which we totally failed on. And we were actually looking at a lot of non-robotics ideas at the time, but this one actually, we kind of found that we found such a strong demand from this first customer we talked to, and then he put us in touch with all of his other friends in the security industry, and we just got such a positive response. Like, wow, yeah, it's going to be a lot harder to do a hardware startup, but like we do have the background for it, and we do have the, it seems like it's a really good problem and space to tackle. But we were basically looking for customers and where they said they had a problem and they would pay money to solve it, and that they would give us a handshake deal that once this is ready, I will pay for it at this price.
Wow.
And we got a couple people to get to that point and do those handshake deals. And that was enough for us to go raise our first funding round of, hey, this is our idea. Don't believe us. Go talk to these customers that have done these handshake deals with us. And let them tell you how excited they are for this product and how they would use it.
Okay. So a few things here are very interesting to me. The first, can you just tell me a bit more in detail about how you did your initial market research when you were talking to people and seeing what they would pay for and this kind of thing? Like, how does someone do that kind of thing? How do you just, I don't know, like, how do you go about meeting these people and what kind of questions and like, what's the heuristic when doing that kind of thing?
Yeah. So what we were looking for was talking to anyone that we didn't know what their job actually entailed. And it's funny when it's not that hard to do. You just kind of have to go and start doing it. And whether that's talking to strangers at Starbucks, which actually isn't that effective, what we found most effective was going through our network and really going and like asking. I asked every single one of my friends, what do your parents do? What do your aunts and uncles do? And, what to people that I knew, like just asking them what their friends did. And like, really kind of
cool.
I made this like kind of list of everyone I knew and went through them and like, tell me about like everyone that you're like close enough to that you could ask for a favor, and like, tell me like, what does your uncle do? What does your aunt do? And we kind of wrote down like, oh, actually, I don't know what being a pharmacist is like. Like, let's go talk to that person. I don't know what being a security director is like. Let's go talk to that person. I don't know what being a lawyer is like. Let's go talk to that person. And then once we were talking to those people, in the back of our minds, we had a couple broad theses that we cared about and that things that we were looking for. They were mainly around enterprise and finding ways that we could use software or AI to make some process better or more efficient or cheaper. And so that was kind of the lens that we were looking at these interviews through. But a lot of it was trying to be very open-ended of like, tell me what you actually do day to day. Like if there's one problem that you could solve or like pay money to solve at work, what would it be? And trying to really focus on the problem. Because a lot of times people will come up with an idea that they want you to do, and it's kind of like people asking for the faster horse. But you have to kind of keep going back and really understanding what is the pain point that they have, like what would it actually need to solve it. And a lot of times from someone saying an idea that they have, you can kind of work back to what is that actual pain point.
What is the pain point?
Come up with an even better idea.
Gotcha. What an interesting thing. Okay. And then the other thing that I'm really curious, so can you talk a little bit about kind of the way that you have been funded at Cobalt?
Yeah, absolutely. So we have great financial backers. Bloomberg Beta did our seed round in 2016. So they're a really good fund focused on the future of work, kind of deciding, their main LP is Michael Bloomberg. And so they really care about helping invent what is work going to be like in the future. Then for our Series A, we raised from Alfred Lin at Sequoia. He
Oh,
was sort
Sequoia,
of
hell yeah.
yeah. So Sequoia is a really, really amazing investor, and Alfred Lin was actually the top of our list of who we wanted to go with for our Series A.
Wow.
He's a really, really incredible individual. He was the COO of Zappos, and it actually helped bring Kiva Robotics into Amazon after Zappos got acquired.
Wow.
By Amazon, and so he's very familiar with robotics. Most importantly to us, he is an operator. He has been in startups and feels the pain, and knows what it's like, with the time pressure and like everything on fire. And we really wanted people like that, people that had been through this themselves and could sort of know what Travis and I were going through, rather than someone that was kind of just a financial analyst that had never been in it themselves and was making a bet on us. And then we raised a Series B from Co2 later, and we've raised around 60 million total.
Wow.
From our Series A's and B's. Co2 is another great investor. Our partner there is Chris Fredrickson. He was very early at Munchery and actually did a lot of really hard work around deliveries and logistics. And that's something that's very hard for us, is we're moving hardware around and shipping around the country and actually across different continents. We actually have customers in Australia and Japan.
Oh, wow.
The UK now. So,
hell yeah.
Logistics are very hard for moving a 5-foot tall robot around. So, but yeah, we've been very, very happy with our investors and have some of the best in Silicon Valley.
I mean, you guys are very promising. So it's wonderful to see great investors supporting you as well. So for someone who wants advice on how to approach investors or how to look for any advice on getting funding, I suppose, that you have.
Yeah. I would say to put yourself in the mind of the investor, and what they're looking for is, how is this going to fail? And they're looking for the startup idea they're looking for a startup where they look at it like, oh, I don't see any possible way this could fail. And so put yourself in that mindset and think, why would an investor say no to me? And then start working on fixing those things. And that might be they think, oh, I don't think this technology is possible. Then go build a prototype. They might say, I don't think people are going to actually want this. Go get customers. I don't think people are going to pay for this. Show that people will pay a high price for it. And so really, think about what the objections are going to be. And then your work as an early stage founder is doing things and collecting evidence to show that this is working.
Yes.
And a lot of that evidence looks like building an early stage business, of getting customers, building a prototype. But really sort of at, in the first year of a business or year or two, the revenue isn't actually important. It's just an indicator that you'll get more revenue in the future. And so you need to be thinking about it in terms of, what does an investor need to see to show that this is a great idea and that people are going to want this and that we're the correct team to build it. Yeah.
So one thing that I have seen many times is people or companies accepting funding, and the funding comes with terms and things that eventually suffocate the company. Can you talk a little bit about avoiding things like this, or just how do you make sure you don't accept bad investment or whatever it might be?
Yeah. So that's definitely sort of a negotiation game. And you just need to make sure that you're in a strong enough point where, even if someone is offering more money, if there are those bad terms in there, you should probably take someone else's money. And being just knowledgeable about it, really reading through the docs and understanding sort of what's happening. Some of the things to worry about are sort of guaranteed returns, or sort of any sort of overhangs where someone can get sort of more than they otherwise would if your valuation is lower. But one of the best things there is to get a really, really good investor on your cap table to start. And then, with us having Sequoia and Bloomberg and Co2, no investor is going to try that because they don't want Sequoia to get mad at them. And so having really, really good partners helps you negotiate, because that new investor you're talking to, your existing investors are on your side in that when you're talking to them. So getting really good partners and really well-known people where they care about their reputation. A no-name investor might give you money, but if they don't have a reputation to lose, if something comes up, they might try to squeeze you for any penny you're worth.
Ah,
Whereas a really well-known and sort of prominent investor like Sequoia, they care more about their reputation with other founders and sort of showing that they're going to do right by people. They care more about that than making a few extra dollars on any deal.
All right. So wrapping up, what advice do you have for, say, like a 20-year-old version of yourself, I guess in now or in back then? How would you do the same thing again a little better? Or what would you wish you, I don't know. Advice for a younger you.
I would say the most important thing is just always keep talking to customers and sort of always stay skeptical. Make sure you're always going to figure out what the pain point is and never sort of stop and think that you've solved something. Because definitely for us, from that first robot to sort of where we are now, so many things have changed, not just about the robot, but in how we are delivering the value to the customer. And those iterations have let us really grow and scale and provide way better value. So I'd say just really stay focused on the customer. The technology and the product is just a means to an end. It's not an end in itself. You need to stay focused on the customer and their pain points.
Awesome. So wrapping up, do you have any links or social media or anything you'd like to share with our listeners?
Yeah, absolutely. I can put in a couple links to some YouTube videos of our robot using elevators with its elevator arm, some links to sort of our hiring page. And we are looking for robotics engineers and web engineers and pretty much everything right now. We have a lot of really strong customer growth, and we're trying to keep up the engineering team with it to help deliver that value.
Awesome. So I'll put links in the video description and podcast description. That sounds good. Thank you. This has been a pleasure.
All right. Thank you so much, everyone.
That's all we have for you today. I hope you enjoyed the episode. I was surprised during the interview that the Cobalt robot is going to be trying receptionist work during the day. What other applications could you think of for a robot like Cobalt's robot? Let me know in the comments on SenseThinkAct.com. Thank you again to our founding sponsor, Open Robotics. Goodbye, everyone.